All right, here we go. We're at the last section of Chapter 3. It's very exciting, and we're going to be talking about related rates. And I have good news for you guys, because every single related rates problem is a word problem, and I know that they're your favorites, so no need to thank me. But this is a really applications-heavy section. This section really kind of brings together everything that we've talked about. So the derivative, implicit differentiation, our derivative rules, understanding the derivative as a rate of change, and it brings them all together in a way that makes sense in the real world. It has very real-world applications, pardon the pun there. So let's just jump right in. We're going to start with example 1 here. This is a classic problem. You'll probably see it in every calculus textbook. It says a 26-foot ladder is placed against a wall. If the top of the ladder is sliding down the wall at 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? So step 1, they're giving us a lot of information. Some of you might even just be able to guess what we want to do. We probably want to draw a picture if necessary. So draw a picture. I'm also going to add in, along with drawing a picture, I want you to use that picture or some other method to organize your information. Because these types of problems are going to give you a lot of information, and we want to make sure that everything is clear and easy to understand. We want to make sure that we know exactly what each value, each number represents in our problem. So I'm going to start by drawing a picture. I have a wall. Here's my ladder leaning up against the wall if you need to draw in that ladder. And then the ladder is resting on the ground. I have created a right triangle. Anytime you can create a shape that is familiar to you, that's always beneficial. So what do we know? Well, we know that the ladder is 26 feet long. So that talks about this side of my right triangle. Along with organizing your information, I'm also going to suggest that you give each of the sides or each of the pieces of our problem that we're talking about. So we're talking about here, we've got a triangle. We want to probably talk about the lengths of each one of these sides. If I want to talk about the lengths of each one of those sides, I should give each one of those sides a variable name. And we'll see why that's helpful in just a little bit. But I'm going to call this side, since it's the hypotenuse, I'm going to call this C is equal to 26. I'm thinking about a squared plus b squared equals c squared. I'm thinking about my Pythagorean theorem. What else do we know? It says if the top of the ladder is sliding down the wall at 2 feet per second. So what's going on here? We have the top of the ladder right here. It's sliding down the wall. I like to draw in little arrows here so that I know exactly what's going on. I can sort of visualize what's going to happen over time. So the top of the ladder slides down the wall. And we're going to talk about this 2 feet per second in just a second here, in just a moment. It says, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? So we would like to know how quickly is this bottom part going to slide to the right here in our case. Since this side right here, this is the ladder. The ladder's not changing in length. It's just going to stay a constant length. So as this side goes down, this side kind of kicks out and gets a little bit longer. So let's see, we know that the bottom of the ladder is 10 feet away from the wall. So I'm going to call that B for bottom. Let's say bottom is 10 feet. So I'm going to say B is equal to 10. This side over here, I don't know this side, but I could figure it out fairly easily. And actually, if you want to, now might be a good time to do that. Maybe we'll say, okay, I know that a squared plus b squared is equal to c squared. So let's see, a squared, I don't know a, that's what I'm trying to solve for. B squared, b is 10 squared equals c squared, that's 26 squared. So if a squared plus 100 is equal to, I believe, 676. Let me just double check. Yes, 676. A squared is equal to then 576, which means that A is equal to, I believe 24, but I want to check my work here. Yes, 24. So A is equal to 24. So this is cool. I know all the sides of my triangle, but that's not really calculus. That's just, geometry. That's, we've seen that problem 1,000 times before. What I really want to talk about here is this rate of change, this 2 feet per second, and I really want to highlight that. It says 2 feet per second. So this is describing how the top of the ladder is sliding down the wall. It's describing how this piece is sliding down. So a couple things I want to think about here. This is really describing the rate of change of this side, of side A. So I'm going to use that rate of change. That makes me think of derivative. I'm going to talk about the derivative of A with respect to time. I'm going to call that dA over dt. And you might be thinking, well, can you slow down there for a second? Why dA over dt? dA, this represents the rate of change of side A, which is this side. That's what we wanted to talk about. So that's the rate of change of side A with respect to time. In every single one of these problems, or at least just about every single one of these problems, we're always going to be talking about how these sides or how these quantities, how our problems are changing with respect to time. Because that's just how we do these problems. We always want to know how these things are changing as time moves forward. Another way that we can actually tell this, right, we can say, okay, with respect to time, look at your units here. 2 feet, so feet talks about the rate of change of A per second. This is the piece I really want to focus on, that per second. That's a unit of time there. So that helps me decide what I'm taking the derivative with respect to. So I'm taking the derivative of A with respect to time. So, okay, what else do we know? Let's clean this up a little bit here. Let's erase this. All right. So we know that this side is sliding down the wall at 2 feet per second. So I would expect most of us to say, well, this side is 2. And you would be almost right. But think about what's happening to this side over time. As time moves forward, what happens to that side? Well, we just said, you know what? The top of the ladder is sliding down the wall. It's going down. So a little bit later on, my ladder is going to be in this position. What's happened to the length of that side? It's gotten shorter. So because that side length is getting shorter, we want this rate of change, this derivative, to be negative. So I'm going to say dA over dt is equal to -2. Because, again, this side right here is getting shorter. And that's something that you can ask yourself in every single one of these problems to determine if your derivative should be positive or negative. You'll look at this piece or whatever it is you're talking about in that problem. You'll say, okay, that side of my triangle, is it getting longer or is it getting shorter? If it's getting longer, then the derivative should be positive. But here in this case, it's getting shorter. Our derivative should be negative. All right, what am I trying to find here? What am I trying to find? It says, at what rate is the bottom of the ladder moving away from the wall? So I want to know, what is the rate of change of the bottom of my ladder? So what's the rate of change of this distance, of side B? So in other words, if we're talking about dA over dt, I want to know, well, what is dB over dt? How is that side changing with respect to time? So dB over dt, this is what I'm trying to solve for. This is what I hope to find out in this problem. You may want to account for all of your sides. So I have A dA dt, B dB dt, C, I think it might be helpful if we had dC dt. So dC dt, that describes how this side is changing over time. So again, I want you to kind of ask yourself, is that side, is it getting longer or is it getting shorter? And it's a trick question because the right answer is actually neither. It's not getting longer or shorter. It's not changing. So if it's not changing, then we would say that the rate of change is 0. It's not increasing, it's not decreasing. So dc over dt must be 0. At this point, we've drawn our picture, we've organized our information. I think this is as detailed as this picture is going to get. And to me, actually, I think that this is the hardest part, drawing your picture and organizing your information. Because you need to digest everything that the problem gives you. You need to look at it and decipher, okay, what does this number represent? What part of my problem is this referring to? What are the units on that? Is this a side or is this a derivative? So at this point, I think the hardest part of our problem is done, which is good. So that was all just step 1. So let me separate these here. Step 2, you need to write an equation, right? An equation that relates your variables. So I want something that relates A, B, and C. We've actually already used that equation, the one I have in mind at least. Don't overthink this. I have a squared plus b squared equals c squared. That's a relationship between a, b, and c. That's an equation that relates all 3 of those variables. So that's going to be my equation. That's what I'm going to use for this problem. I'm going to use a squared plus b squared is equal to c squared. And as soon as you find that equation, that's awesome. We are going to move on to step 3. Step 3, we want to differentiate with respect to time t. So I'm going to take this equation that I just wrote in step 2, and I'm going to take the derivative of it with respect to time. So essentially what I'm going to say is I'm going to say I want to take the derivative of a squared plus b squared is equal to c squared. I want to take the derivative of this equation with respect to time right here. And this can be a little bit tricky, but once we see a few, I think we'll get the hang of it pretty quickly. Each of these sides, a, b, and c, those are really functions of time because the side lengths, right, we said over here, the side lengths A, B, and C, these are all changing as time progresses, as time moves forward. So these are all functions of time. So these are all functions of time, which means I need to take the derivative implicitly with respect to t. So what that is going to look like here is I'm going to take the derivative of a squared, which you would tell me using my power rule is 2a, but then I need to multiply by the derivative of a with respect to time because I'm using, again, implicit differentiation. This is where implicit differentiation comes into play. So I'm going to multiply that by the derivative of a with respect to time. You could also say a prime, but I think that this is a lot clearer and easier to read than saying 2a times a prime, and then I think it's easy to mix these two up. So that's why I'm going to use dA dt instead of a prime. So I have 2a dA over dt plus 2b dB over dt. Again, I'm just taking the derivative of b squared, which is how I get 2b, and I'm taking the implicit derivative with respect to time, so I have to multiply that by dB over dt. Lastly, derivative of c squared, well, that would be 2c, but again, I'm using implicit differentiation here, so I need to multiply that by dc over dt. Once you have your derivative, that's all I need from this step. So you're going to take the derivative of your function with respect to time. You're going to use implicit differentiation to find your derivative with respect to t. The rest of this problem is actually just going to be a little bit of algebra. So if I look at step 4, I'm going to do some substitution. And where am I going to look? I'm going to look back at step 1. Because I have all of this information. Whoops, I erased that. I have all of this information. Oops, I meant to highlight that. Very clearly laid out. This is why I think that first step is so important. I know what A is. A is 24. I know what dA over dt is. That's -2. I know what C is. I know what dC dt is. I know what B is. I don't know what dB dt is, but that's what I'm trying to find, so that's okay. So I'm going to take the derivative that I just found, which is 2a dA over dt, plus 2b times dB over dt equals 2c times dC over dt. And I'm going to plug in all of my information. So what do we know? We know A is 24 times dA over dt, that's -2, plus 2 times b is 10. dB dt I don't know, but I'm going to leave that as simply dB dt because that's what I'm trying to solve for, is equal to 2c. What did we say c was? We said c was 26. So 2 times 26 times dC dt, that's 0. So we're going to do some substitution, and then we are going to solve the resulting equation. So let's see, 2 times 24 times -2. Let's see, I should have -96 here, plus 2 times 10, I've got 20 dB over dt. Over here, 2 times 26 times 0, I'll just have 0. 20 dB over dt equals positive 96. We'll finish up over here. So dB over dt equals 96 over 20, which we could simplify that fraction, or we could simply say that that is 4.8. I'd also like to give a unit, and for that, just look at your derivative. What are the units of b? What are the units of your numerator? Well, b was the side of my triangle. It was a distance, so that was feet per unit of time. What's our unit of time here? We said feet per second earlier, and we can double check here with our prompt. We said 2 feet per second, so we seem to be pretty consistent with our answer, or with what the problem gave us. So 4.8 feet per second. There is my dB dt. So at this point, I'm just about done with my problem. I've found dB dt, which is what I wanted to look for. Step 5, I'm just going to encourage you to check your answer here. Check your answer. And the two things that I'm going to ask you to check here, you want to check the sign of your result, and you want to check the units of your result. Do they make sense? So here, we ended up with a positive 4.8. Does that make sense for our problem? Well, let's go look at our triangle, and let's erase some of this stuff. dB dt, that's the rate of change of this side right here. What's happening to this side? We said over here it's getting longer. So if the rate of change is positive, that side is getting longer. That seems to make sense. If we have a positive derivative, that side is getting longer. Feet per second here, that's describing the unit of change, or the rate of change of b with respect to time. So feet per second, yeah, I think that makes sense. So dB over dt equals 4.8 feet per second. So dB over dt equals 4.8 feet per second seems like a very reasonable answer. So this was, I think, a pretty challenging one to start off, but it does a really good job of showing that first step, which I actually think is the hardest, but it's also the most important. Drawing your picture and organizing your information makes the rest of the problem so much easier to do. So I'm really big on organizing your information for these kinds of problems. So I would encourage you to practice some of these. In the next videos, we'll look at some simpler examples that are a little bit easier to digest, I think. But this does a really nice job of showing why organizing your information is so important at the end of your problem.